Let's continue discussing about describing functions. Second, in the last session we found out the describing function of on-off nonlinearity. Today we'll find out the describing function of the hysteresis nonlinearity. Fine. So hysteresis nonlinearity can also be considered as an on-off nonlinearity, on-off relay with hysteresis. Let's see first of all the behavior of the hysteresis nonlinearity. We have a system this is what a hysteresis loop looks like, and let the magnitude of this system be plus minus m, and the magnitude of and let the hysteresis bandwidth be let it be between plus minus h. Now what we are doing is we are applying an input of we are not actually applying we are applying a sinusoidal input. We are applying a sinusoidal input x equal to x sine omega t, small x equal to capital X omega t, and so this is a sinusoidal waveform and input having a magnitude of x. I'm drawing the omega t axis in this direction. Fine. This is your magnitude direction. This is the magnitude direction. The x omega t is downsides. So this is your point pi. This is your point 2 pi. So if you map the hysteresis function onto this onto this sinusoidal waveform, you will see only for a brief range. That's, say for example, this angle is alpha here. This will be therefore pi minus alpha. We are actually assuming a ideal hysteresis loop, and similarly here you have pi plus alpha, and you have 2 pi minus alpha. Fine. So this is your system here, and this alpha, if we map the system this is your this is angle alpha, so corresponding to the bandwidth of h, you can say that alpha is equal to sine inverse of h by x. Fine. So when you map these two, you are basically getting this type of output from alpha to pi plus alpha, and then from pi plus alpha to 2 pi plus alpha. So this is your output waveform. So on the same lines you can say that prior to alpha the magnitude was actually minus m, right? So this is your y versus omega t. So y of omega t is actually this kind of waveform. So what happens in this case is starting from alpha you can say that your output will produce positive value, and until the system basically reaches to a magnitude of minus h when it retraces the path until it reaches minus h, that's actually corresponding to pi plus alpha on the input axis. The system output will remain to be a positive value, that is m. Fine. From minus h then back to h, you will again see that the system will be having the value of minus m. Therefore y of omega t is equal to minus m for 0 to omega t to alpha. It's equal to plus m for alpha to omega t to pi plus alpha, and it's again equal to minus m for pi plus alpha to omega pi plus alpha to 2 pi plus alpha. Fine. In other words, we can simply state that for when the input exceeds the value that's h, the band of the hysteresis loop, the output will assume plus or minus m on either side of the zero axis on the of the x-axis, y-axis. Right. So here you can see y omega t is basically a shifted waveform, and it's actually shifted by an angle of alpha, and it's either odd, it is neither odd nor it's an even function. So this is our y omega t, and we can see that this is neither an odd function nor an even function, and you can see it as a half wave symmetry. It is symmetrical about the half wave. So therefore the Fourier series expansion for the fundamental component, we need to determine both a1 and b1. In this case a1 is equal to 2 by pi 0 to pi y omega t cos of n omega t d omega t. Fine. Which gives us which is equal to 2 by pi zero to alpha minus m cos omega t d omega t plus alpha to pi m cos omega t d omega t. So is equal to 2 by pi. So integral, solving the integrals, 2 by pi integration of cos of omega t is minus sine omega t. So this becomes 2m by pi minus sine omega t to alpha plus 2m by pi 4m by pi sine alpha. So in a similar manner, we can write down b1 will be equal to 4m by pi. A1 was minus 4m by pi sine alpha. It will be 4m by pi cos alpha. Once you solve this, so y1 will be, the magnitude will be a1 square plus b1 square, which is equal to under root of 4m by pi sine square alpha plus 4m by pi square cos square alpha. That actually is 4m by pi. So this is the magnitude of y1. Similarly, the angle phi1 will be tan inverse of a1 by b1. So tan inverse of a1 by b1, which will give us minus alpha. So therefore we can write nx, the describing function, as it's the ratio of the output by phase divided by x, which implies y1 is 4m by pi x and phi1 is minus of alpha. So this is our transfer function, 4m by pi x angle minus alpha. We have already seen, as already said to you, that alpha will be equal to sine inverse of h by x. So this is your angle phi1 equal to sine inverse of h by x. So this is the describing function of our hysteresis nonlinearity. So if we plot